mentioned, this is the second of 8 lectures on seismic design. Today, we will start getting into seismic design itself. The topic, as you see, is seismic design by BNBC 2020. And we will specifically discuss the details of the equivalent lateral force procedure, which is the procedure used most of the time for seismic design. I have maybe 5 or 6 slides from the last presentation that I included here just to remind you of the basics that are already discussed. First of all, in an earthquake, the foundation begins to move all of a sudden and in every which direction. The mass of the structure, which is mainly concentrated at the floor and the roof levels, cannot readily follow the movement of the foundation unless it is a very short, stocky structure. The mass stays behind and then tries to catch up. The force that in a way keeps the mass behind is an inertia force. So the reason that the mass does not readily follow the movement of the foundation is that it is subject to an inertia force, the direction of which is opposite to the direction of the earthquake ground motion. Okay. So a structure subject to a ground acceleration in an earthquake, U sub G double dot. U sub G is displacement of the ground. Single dot is first derivative with respect to time, which would be velocity. The double dot is second derivative with respect to time, which would be acceleration. So a structure with its base subject to ground acceleration is equivalent to a fixed base structure, the mass of which is acted upon by an inertia force equal to the mass times the acceleration, and the negative sign indicates that the direction of the inertia force is opposite to that of the earthquake ground motion. Okay. Now here we are assuming that the acceleration of the mass is the same as the acceleration of the base. That is not necessarily always so. There is amplification of the ground acceleration as we go up a building, typically. And this is what we are saying on the next slide. In some circumstances, dynamic amplification due to near resonance, that's a concept we discussed at length the last time, can increase the building acceleration to a value 2 or more times that of the ground acceleration at the base. And obviously, a structure may have more than one level. So there will be masses at the various floor levels and the roof level, and those would be accelerated in an earthquake, developing inertia forces. Here we are looking at a multi-story building where, let us say, the roof level slab is being acted upon by these inertia forces due to earthquake. Okay. So the direction of earthquake is from left to right. The inertia forces are from right to left. This slab, when subject to those lateral forces, will act like a deep beam in its own plane. And when it does that, this is called a diaphragm. So compression will develop along this edge of the diaphragm. Tension will develop along the opposite edge, which has to be taken by what we call cord reinforcement, which we'll have to provide. And then along edges parallel to the inertia forces, we have shear developing. Those shear forces will be transferred to the supporting frames or shear walls, which will take them down to their foundations, and then the foundations will transfer the forces down to the soil underneath the structure, where all loads ultimately belong. Okay, so this picture tells you the concept of the load path. In this case, the inertia forces are going through the diaphragm to the vertical elements of the seismic force resisting system, as we call them, the columns and the shear walls, which take them down to their foundations, and the foundations transfer them to the ground underneath the building. So very important concept of load path. From point of load application or origin down to soil underlying foundation. It is very, very preferable in seismic design to have direct load paths, which will be provided by simple building configurations. If we have too many setbacks, projections, this and that, then the load paths are complicated, and that is to the detriment of the structure. We also very much like to have multiple load paths rather than just one, and that is the concept of redundancy. BNBC seismic provisions are compared to ASCE 7. I don't want to say incomplete, but major topics are simply not covered. Redundancy is one of them. Redundancy is mentioned, but the ASCE treatment of redundancy is not to be found in BNBC 2020. Before I'm through with the 8 lectures, I will talk about some of those major topics that are essentially not covered in BNBC, which I think you need to know about in order to have a rounded idea of seismic design. Now, this all-important diagram is the last one I have repeated from last week. Here we have the load displacement response of a particular structure to a particular earthquake. The forces developed in the structure as it goes through the earthquake are along the y-axis, and the lateral displacement suffered by the structure, again, as it goes through the earthquake, are along the y-axis. This picture tells you that seismic design is essentially an exercise in trade-off between strength and what we call inelastic deformation capacity. We have a choice of designing our structure for a high level of strength, in which case its load displacement response would be elastic. There will be no damage associated with it. We will get the structure back intact once the earthquake passes. And in that case, there is no need for significant inelastic deformation capacity. We, however, typically like to design for a much lower strength level than would be required for elastic response of the structure. And if we do that, then part of the displacement suffered by the structure is inelastic. It has damage associated with it. The earthquake passes, we don't get our structure back intact anymore. In order to avoid collapse, these inelastic deformations must be within the inelastic deformation capacity of the structure. And inelastic deformation capacity is the range of inelastic deformations over which full factored gravity loads can be sustained. If full factored gravity loads can be sustained over a long range of inelastic deformation, the structure has large inelastic deformation capacity. If the full factored gravity loads can be sustained only over a short range of inelastic deformations, then the structure has low inelastic deformation capacity. Okay? Inelastic deformation capacity comes from proper detailing of the members and the joints. So if we want to design for a low, hello. So
Yeah, Douglas.
yeah,
You can continue.
somehow there was an echo.
Yeah, I removed it.
Okay, good.
Yeah.
So if we want to design for a low strength level, we would need a high degree of inelastic deformability, which would mean fancy detailing of the structural members and joints. And if we are content to design for a high strength level, then we need only cruder detailing. We don't need a high degree of inelastic deformation capacity. Seismic design is always a two-part affair. Design for the forces that we have chosen to design for the strength level, and detailing for the inelastic deformation capacity that we must have in order to be able to design for the force level that we have chosen. So the design forces are given in the code, and you will see in BNBC, it is part 6, chapter 6. And the detailing requirements are also given in the code. It's part 6, chapter 8 of the BNBC. We will talk about the forces and related items today and tomorrow. And then on Wednesday and Monday of the following week, we will talk about detailing. Okay? So the design force level of the code and the detailing requirements go hand in hand. Okay? I would absolutely like you to understand this, that the seismic design is a two-part affair. You design for the forces, but you also detail for inelastic deformation capacity. It has never been otherwise. And the parameter that indicates whether we would need fancy detailing or cruder detailing is the R factor, which goes into the denominator of the design base shear. The higher the R, the lower the design base shear, the lower the strength we are designing for. So we would need fancy detailing called special detailing, and the higher the R, the lower the R, the higher the design force level, the lower the need for inelastic deformation capacity. So we can go for much cruder ordinary detailing. In between, there is intermediate detailing. Okay, so those are the very basics. With that, we will discuss seismic design specifically by BNBC 2020. The seismic provisions of which are essentially based on ASC 705. Now, unlike in many other cases, live load or even wind, pretty significant modifications have been made to ASC 705. in the main body of BNBC 2020. And however, this is kind of interesting. BNBC says, this is the section number 2571, alternatively, for buildings with natural period less than or equal to 2 seconds, so not for very tall buildings, the seismic design base shear can be calculated using ASCE 702 with seismic design parameters as given in Appendix C. Okay, so if you go with Appendix C, you are basically doing ASCE 7 seismic design, and that is fully permitted by the BNBC. Okay. Now the curious thing is, if the whole thing is based on ASCE 705, why is the reference to ASCE 702, the prior edition? And there is no no satisfactory answer that I have found. It probably should have been ASCE 705. The section 2571 goes on to say, however, the minimum value of S sub A, the spectral acceleration, as you will see, should not be less than 0.44 S sub ds times I, the values of S sub ds, etc. Now, interestingly, that restriction, that S sub S shall not be below a certain value, is already built into ASCE 702. It is not in ASCE 705. So this reference to ASCE 702 does not make a lot of sense. It probably was meant to be ASCE 705, and somehow got mixed up. It is my guess. So in this presentation, I will go mainly with Appendix C, which is ASCE 705, but I will relate back to the provisions in the main body of BNBC section 2.5, and you will see that the two are the same. It gives you the same results, whichever whether you go with the appendix or you stay with the main body of BNBC 2020. Okay, the code part 6, chapter 2 is loads on buildings and structures. Within that, section 2.5 is earthquake loads. So that is essentially our section today. Part 6, chapter 2, section 2.5. Section 2.7, which we discussed last week, combination of loads, obviously get into the picture if we want to do design. Any kind of design involves combinations of loads. Appendix C is entitled Seismic Design Parameters for Alternative Method of Base Shear Calculation. So in BNBC, we will use all those sections. Section 2.5, earthquake loads, 2.7, combinations of loads, Appendix C, seismic design parameters for alternative method of base shear calculation. In ASCE 705, the seismic provisions are in chapters 11 through 23. If you want to relate to the IBC, ASCE 705 was adopted by 2006 as well as 2009 IBC. The section number is 1613. 1613 of the IBC talks about seismic design forces. Those are taken from ASCE 7. Okay, so that tells you, gives you a kind of a complete picture. And then part 6, chapter 8 has the detailing requirements, detailing of reinforcement in concrete structures. That is for all concrete structures. If you want earthquake-resistant detailing requirements, those are in section 8.3. So we will make use of them, not today, but starting on Wednesday. Now, BNBC, I would say, unlike most codes, it gives you general principles and some advice of what is good for an earthquake-resistant structure. This we typically don't do with our codes. As years have gone by, we have become more and more rigid about the code containing only enforceable requirements. Anything that is not enforceable does not belong in the code. You can put it in the commentary or support literature, whatever, but it doesn't belong in the code. BNBC is not in that camp. It has quite a bit of stuff that is not enforceable. BNBC doesn't have a commentary. That may be one reason why you find this material in the code itself. The general principles of seismic design by BNBC 2020. This paragraph, I would say, belongs. It is background, but then you will see there is other stuff that is not really code material. The purpose of earthquake-resistant design provisions in this code is to provide guidelines. Now, code doesn't provide guidelines. A code gives you mandatory requirements. Okay? So anyway, so the purpose of earthquake-resistant design provisions in this code is to provide guidelines for the design and construction of new structures subject to earthquake ground motions in order to minimize the risk to life for all structures, to increase the expected performance of higher occupancy structures as compared to ordinary structures. Higher occupancy structures would be like hospitals or police stations and things like that, and to improve the capability of essential structures to function after an earthquake. So quite a bit is said here. Minimize the risk to life for all structures, to increase the expected performance of higher occupancy structures as compared to ordinary structures, and to improve the capability of essential structures to function after an earthquake. It is not economically feasible. This is important. It is not economically feasible to design and construct buildings without any damage for a major earthquake event. The intent is therefore to allow inelastic deformation and structural damage at preferred locations. Yes, we'd like to choose the locations of damage at preferred locations in the structure without endangering structural integrity. That is very important. The structure should still be standing up, although it is damaged, and to prevent structural collapse during a major earthquake. Okay? So that gives you the principles which are very, very important. We are not designing for elastic response to the design earthquake. We deliberately allow inelastic deformations at selected locations under the design earthquake, but we have to make sure that the inelastic deformations are within inelastic deformation capacities so that we do not have collapse. We do not have problems with structural integrity. Now, this is the material that, as I indicated, does not belong in the code, but this is good stuff. So I think we should. I kind of want to point this out by reading, and this is 3 or 4 slides, not a whole lot. So, characteristics of earthquake-resistant buildings. The and I wouldn't read them except unless they were really full of very good sense. The desirable characteristics of earthquake-resistant buildings are described below. Structural simplicity, uniformity, and symmetry. All three are important. Simplicity, uniformity, symmetry. Structural simplicity, uniformity, and planned symmetry is characterized by an even distribution of mass and structural elements, which allows short and direct transmission of the inertia forces created in the distributed masses of the building to its foundation. Okay? You keep building simple, uniform, and symmetrical in order to have short and direct load paths. A building configuration with symmetrical layout of structural elements of the lateral force resisting system and well distributed in plan is desirable. Uniformity along the height of the building is also important, since it tends to eliminate the occurrence of sensitive zones where concentrations of stress or large ductility demands might cause premature collapse. So all of this is very, very good advice, except that most real buildings violate these principles. There are owners involved, there are architects involved. The architects want their building to look distinctive, not like a rectangular box. So they don't have a lot of taste for this simplicity, uniformity, symmetry, etc., etc. And tomorrow we will have an elaborate discussion of structural irregularity and how we deal with those in seismic design, because we have no choice. We as engineers will be forced to deal with structural irregularity. Most of the buildings we design will not be simple, uniform, and symmetrical, but those are definitely desirable. To the extent that they are very helpful. So, continuing, some basic guidelines are given below. With respect to the lateral stiffness and mass distribution, the building structure shall be approximately symmetrical in plan with respect to two orthogonal axes, okay, doubly symmetrical. Both the lateral stiffness and the mass of the individual stories shall remain constant or reduce gradually without abrupt changes from the base to the top of a particular building. Okay? So the lateral stiffness and the mass of the individual stories shall remain constant or reduce gradually without abrupt changes from the base to the top. Quite a few things are said. Decrease gradually without abrupt changes. You go to a place like Dubai, you will see all the buildings violate all these principles. Okay, the buildings have larger plan as you go up. So instead of decreasing, reducing gradually, things increase. And anyway, all I'm trying to say is real life is different from the principles that are given here, but the principles are nonetheless good. Definitely, that's what you should aim for. All structural elements of the lateral load resisting system, such as cores, structural walls, or frames, shall run without interruption from the foundations to the top of the building. That again, quite often does not happen. Every owner in the world wants the lowest stories of their building kind of open for commercial reasons. And then the upper parts typically are offices, hotels, apartments, whatever. And there is no problem with having shear walls in those portions. So the shear walls in the upper portions of a building are discontinued as they come down for functional reasons, for commercial reasons. So yeah, however desirable it is, you don't always get the structural walls and frames running without interruption from the foundation to the top of the building. When they do, we are lucky. When they don't, we have to deal with that fact. An irregular building may be subdivided into dynamically independent regular units, well separated against bounding of the individual units to achieve uniformity. Can be done. That is an expensive solution, and that is a headache through the lifetime of the structure. I do not know that that should be a recommended solution most of the time. There are situations where that may be quite viable, but generally no. The length to breadth ratio, the plan dimension ratio of the building, long side to short side ratio of the building in plan shall not be greater than 4. Okay. Now that I agree is desirable, and this one you probably will get most of the time. But anyway, so those are desirable characteristics. Now, the actual discussion of seismic design, I have divided it into parts just for convenience. These parts do not have any significance of any kind. Part 1 is seismic input parameters, the parameters that are involved in seismic design that are related to earthquake ground motion. Okay. So the section that concerns us here is 2.5.4 of BNBC 2020, earthquake ground motion. Also, Appendix C, seismic design parameters, etc. Appendix C is closer to ASC 705 than Section 2.5.4, as I indicated earlier. Both Appendix C and Section 2.5.4 use seismic zones and the same seismic zone map, which is figure 6.2.24. You will see it several times. Both approaches yield the same design base shear. That is extremely important. It is not that you are getting different designs. Both approaches yield the same design base shear. Okay. Now, ASC 705, and I will go back and forth during the course. Hopefully, I have used blue for BNBC, black for ASC 7. Hopefully, it will keep you from getting confused. And the titles always say which document we are with. Okay, so this is the design response spectrum, as it is called. That itself I will discuss not next week, but week after next. This design response spectrum, the concept of it. Anyway, so this figure shows you the design response spectrum of ASC 705. Okay. So spectral acceleration is on the y-axis. The period of the structure is on the x-axis. The period, in a way, we discussed the last time. The spectral acceleration is really not discussed, except I said it is close to but not exactly equal to the maximum acceleration of elastic single degree of freedom systems. The significance of spectral acceleration is you multiply that by the mass of the structure, you get base shear. Okay, so essentially this is a plot of base shear versus period that we use as the basis of seismic design. We pick the base shear from here, and that is the strength level that we are building into our structure. Okay. So the spectrum, the design spectrum of AC7 is defined by a flat top, which in turn is defined by S sub ds. S sub ds is ordinate to the design spectrum at a period of 0.2 seconds. So it has a flat top, a descending branch, which is defined by S sub d1, the ordinate to the spectrum at a period of 1.0 second. And then the descending branch ends at a long period, transition period, as it is called, T sub L. And then the remainder of the spectrum varies with 1 over T squared. Okay. This is not considered a branch. This is a ramp building up to the flat top. Okay. This is the constant acceleration part of the spectrum for those into structural dynamics, and we will discuss that a week from today. Yes. Anyway, next week we will discuss that this is the constant acceleration part of the spectrum. This is the constant velocity part of the spectrum. This is the constant displacement part of the spectrum, but that's kind of irrelevant now for our purpose. Okay. The period where the ramp meets the flat top is T sub 0, where the flat top meets the descending branch is T sub S. Okay. And T sub L I have already indicated to you. This is the BNBC spectrum. On the y-axis is C sub S, which is pretty close to the S sub A, and I will make it very specific as we go. Between S sub A and C sub S, the way AC7 and BNBC use these two notations there, it's quite confusing. So I will try to clear that up. Anyway, you see that the spectral shape is very much the same. Okay, this T sub B was T sub 0 in the AC spectrum. T sub C was T sub S, where the flat top meets the descending branch, and this T sub D was T sub L. Okay, so it is the same shape, but obviously described a little differently. So this is a direct, I don't know, call it comparison what. So what is T sub 0 of the AC705 spectrum is T sub B in BNBC 2020. That doesn't mean they're identical periods. All I'm saying is that one takes the place of the other. Okay. What is T sub S in the AC spectrum is T sub C in the BNBC spectrum, and what is T sub L in the AC spectrum is T sub D in the BNBC spectrum. Okay. Now, the AC7 spectrum, as you saw, is defined in terms of S sub ds and S sub d1. And S sub ds, I indicated to you, is ordinate to the design spectrum at a period of 0.2 second, and S sub d1 is disordinate to the design spectrum at a period of 1.0 second. If we know those two, we can draw the spectrum, except we also will have to know T sub L, the long period transition period. Now, the all-important quantities S sub ds and S sub d1 are not given directly anywhere in ASCE 7. What we are given are two related quantities, S sub s and S sub 1. S sub s related to S sub ds, S sub 1 related to S sub d1. S sub s is the mapped maximum considered earthquake spectral response acceleration at short periods for site class B. Quite a mouthful is said here, and this is all important. S sub s is mapped. It really means that the values that appear on a map issued by US Geological Survey. Mapped maximum considered earthquake. I will define that, but note that we are not talking about the design earthquake, which is different. Spectral response acceleration, which I said is directly related to base shear at short periods, does not say specifically at 0.2 second period, but that's what it amounts to. Whenever you see at short periods, it is specifically at a period of 0.2 second. There is a reason why the language is this way, but I won't go there. And site class B, that refers to the different site classes that are defined in AC7, site class A, B, C, D, E, and F. These are counterparts in BNBC 2020. Okay. So site class B is the benchmark site class on which USGS, US Geological Survey does all their mapping. So again, S sub S is mapped, maximum considered earthquake, spectral response acceleration at a period of 0.2 second for site class B. S sub 1 likewise is mapped, maximum considered earthquake, spectral response acceleration at a period of 1 second, also corresponding to site class B. Those quantities are given on maps that are part of ASC 705. But if you are doing design in the US, you would go to the US Geological Survey website and find significantly more accurate values than are obtainable from paper maps. Okay. Now, this is kind of in the old days. Today, we have a so-called hazard tool issued by ASCE that gives us the design quantities. We don't have to go to the USGS website. But anyway, for Bangladesh, you don't need the US values, so it's besides the point. But the point that I'm trying to making is S sub ds and S sub d1 are quantities derived from this S sub s and S sub 1, which are the basic quantities. Now, Bangladesh has this zone map, which in the US has been discontinued beyond the Uniform Building Code. The country is divided into 4 zones. The yellow is zone 2, the green is zone 1, the purple is zone 3, and this is zone 4, the pink. Okay. The pink zone, zone 4, has a Z factor of 0.36. The next lower is 0.28. Then for zone 2, which is Dhaka, it's 0.20. And then zone 1 is 0.12. So we have a Z factor to go with each of the seismic zones. Now, in Appendix C, in that specific table, 6.C.1, we are given the S sub S and S sub 1 values for each of the seismic zones. So if you are doing design by BNBC, instead of going to the US Geological Survey website or anything like that, all you need is this table. So you have the zone map for Bangladesh, seismic zone map, and this table in Appendix C tells you that if your site is in Zone 2, Dhaka, then your S sub S is 0.5 and S sub 1 is 0.2. Very simple. There are no contours and things like that. Okay? Now, in BNBC, the S sub 1 is always 40% of S sub S. The long period spectral acceleration at a period of 1 second is 40% of the short period spectral acceleration. S sub 1 is not independent of S sub S as in ASC 705. Okay. S sub 1, as I mentioned, no, maybe I did not mention. S sub 1 is the MCE level peak ground acceleration. Or let me put it this way. S sub S, the short period spectral acceleration, is 2.5 times PGA, peak ground acceleration. Okay, this is from basics, let us say. Okay, and I will show you some of those basics in a week from now. Now, so S sub S divided by 2.5 is MCE level PGA, because S sub S is MCE level by definition. Now S sub S by 2.5 is S sub 1. So S sub 1 is PGA, MCE level PGA. And that is what is denoted by Z in ASC in BNBC 2020. So when you see the Z factor, as you saw on the maps, 0.36, 0.28, 0.2, 0.12, those Z values are essentially S sub 1 values. You multiply those by 2.5, you get your S sub S values. Okay? So these are the values of Z, as you see on the map. You multiply those by 2.5, you get the S sub S values. Now, to make things simpler for you, for most important communities in Bangladesh, you have the Z values given in this table. Okay? So you don't even have to go to the map. Okay? You look up Dhaka, your Z is 0.2. That indicates your zone is 2, and you can readily determine the S sub S and S sub 1 value. S sub 1 is 0.2 and S sub S is 0.5. S sub 1 is the same as the Z factor, as I pointed out. Okay. So the table is just to make things simple. The site class, which is called soil type in BNBC, site class definitions, well, these are maybe not definitions, but in AC7 there are 6 site classes, as I mentioned. A is hard rock, B is softer rock. Hard rock is characteristic of the eastern United States, which is older, geologically older, and therefore the rock is harder. Class B is like California rock, softer rock, which is to be found in the newer parts of the United States. Class C, very dense soil and soft rock. D is stiff soil. E is soft soil. F is soil so poor that to be able to design or build anything on it, we need site-specific evaluations. Okay, nothing can be generalized about class F soils. We have to go site-specific. Okay. Now, what is site class A of BNBC is soil type SA. I'm sorry, what is site class A in AC7 is soil type SA in BNBC, B is SB, C is SC, D is SD, and E is SE. The site class F, on the other hand, is not SF. It has been divided into S1 and S2 in BNBC. Okay, so that gives you direct correspondence. Now, I mentioned that in AC 705, the benchmark site class is B. Everything is mapped for site class B. In Bangladesh, BNBC, the benchmark soil type is A, rock. The seismic zone map is for soil type A or rock. It is specifically set. So the benchmarks are kind of different. AC7 says specifically site class D must be used when the soil properties are not known in sufficient detail unless the building official determines that site class C or F is likely to be present at the site. Now, site class determination we will not talk about, but it is based on measured properties of the soils at the site. And AC7 very specifically says the top 100 feet of the site, 30 point some meters. Okay. So site class is based on measured properties of the soil at the site over the top 30 meters or so of the site. The preferred property to be measured is shear wave velocity. If that cannot be measured, then we can go with either the standard penetration resistance or blow count or undrained shear strength. AC7 makes it very clear that there is no clear equivalence among these properties, that if based on shear wave velocity, a site turns out to be C, based on standard penetration resistance, the same site may turn out to be D. There is no equivalence. Okay, and we allow the standard penetration resistance or the undrained shear strength, basically because the shear wave velocity is not always easy to determine. Depending upon the place, you may not have a contractor able to do that. Okay, so and that makes it important that there be a default site class where there are no soil property measurements. Then what is the site class? And this is what it is about. Site class D must be used when the soil properties are not known in sufficient detail, unless the building official determines. If the building department tells you that they have indication that class C or F soil exists, then that becomes the default site class, not D. But otherwise it is D. BNBC does not have an equivalent statement. I do not know why, but it does not. I looked for it, didn't find it. I verified with Dr. Rakib and he tells me it's simply not there. Okay. So S sub S, S sub 1, we know how to find it for any Bangladesh location. Okay. So you go to the zone map The Z factor is the S sub 1. You multiply that by 2.5, you have your S sub S. That is probably the simplest. Now, site coefficient. BNBC has one soil factor S. AC7 has two site coefficients, F sub A, short period. The sub A is acceleration related. That means it is a short period. F sub A would apply to the short period spectral acceleration. And F sub B is the other site coefficient. Sub B means velocity related. That is the long period site coefficient that will apply to the long period ground motion S sub 1. Okay. So the values of F sub A are given in this table in AC7. I would like to point out that B is the benchmark site class. So for B, all the coefficients are equal to 1. More importantly, the coefficients depend not only on the site class, but also on the intensity of ground motion. Okay. For the same site class E, you see when the ground motion is low, the amplification F sub A is high. And as the ground motion increases, the intensity of ground motion increases, we are looking at lower and lower amplification factors. These are all based on observations. Okay. So very importantly, the site coefficient is a function not only of the site class, but also of the intensity of ground motion at the site. So these are the short period site coefficients F sub A. And then, well, there are a couple of nodes where we said node B and there was a node A someplace. I don't remember. Here, that's node A. So A says that you can interpolate between the tabulated values. Node B, very importantly, says values shall be determined in accordance with 11 force. So if you have the very soft soil, the F, then you have to have site-specific analysis in accordance with section 1147 of AC7. These are the long period site coefficients F sub B. Again, benchmark site class B, all the coefficients are equal to 1. The coefficients are a function not only of the site class but of the intensity of ground motion at the site, as you see here. And notice that on softer soil, not softer soil, on softer soil, when the ground motion is low, in low seismic areas, the amplification is extremely high. This is 3.5. But on the same soft soil, if the ground motion is strong, as would be the case in high seismic areas, then the amplification is lower. Okay? So lower intensity ground motion would be amplified to a higher extent by overlying softer soils, but high intensity ground motion would not be amplified to the same extent. This tends to be quite important. Now, the interpolation between tabulated values and also the site-specific analysis according to 11.4.7. Now, in BNBC, the F sub A values are given in this table, 6.C.2, and these are the values. Some things are kind of interesting here. The values depend only on the site class, not on the intensity of ground motion. For all four zones, we have the same values: 1.21, and 1.15, 1.35, 1.4. These short period site coefficients are called the soil factor S in BNBC 2020. S sub S is no different from F sub A, the short period site coefficient. As I just mentioned, it depends only on the site class, no dependence on zone or intensity of ground motion. Okay, so F sub A, as given in this table, is also the soil factor S of BNBC 2020. F sub B is given in this other table of the appendix, 6.C.3, and F sub B values are also dependent only on the site class, not on the intensity of ground motion. Okay. We are not exactly sure how these F sub V values were derived at. This is F sub V over F sub A. I suspect that somebody decided to go with those ratios and that produced the F sub F values. And I did not point out the last time, but I should have. SA is the benchmark site class. Okay, this is why you have a soil factor of 1 with SA, and the same thing is true of long period ground motion. Okay, this very important table in BNBC 6.2.16, 6.2.16 gives you the basically your ability to construct the design spectrum, site-dependent soil factor, and other parameters defining elastic response spectrum. So for the 6, 1, 2, 3, 4, 5 soil types, you have the S factors given, which are essentially the short period site coefficients, and you have those milestone, the transition points given. Remember, B, C, and D. B is comparable to T sub 0 of AC7. C is comparable to T sub S, and T sub D is comparable to T sub L. So those values are given. So with that table, we should be able to, oh God, I don't know what happened. Okay. So with this table, we should be in a good position to construct our spectrum. Now, going back to ASC 7, we find S sub S and S sub 1 for a particular location. Let us say from USGS website. We determine F sub A. So at the beginning of the seismic design, we have to determine our site class. And then we figure out S sub S and S sub 1 by going to typically USGS maps. Then we multiply the short period map quantity S sub S with the short period site coefficient F sub A, obtaining S sub MS, soil modified short period ground motion parameter. Okay. The difference between S sub S and S sub MS is S sub S is for site class B, S sub MS is for our particular site class. Both correspond to the maximum considered earthquake. That hasn't changed. We likewise multiply the long period site coefficient S sub 1, which we found from USGS website, by the long period site coefficient F sub V, obtaining S sub M1, soil modified long period ground motion parameter. The difference between S sub M1 and S sub 1 is that S sub 1 is for site class B, S sub M1 is for our particular site class. Okay. And then in design, we use 2/3 of the soil modified maximum considered earthquake values. 2/3 of S sub M1 is S sub D1, the design short period spectral acceleration, and 2/3 of S sub MS is S sub DS, the design short period spectral acceleration. Okay, so our design quantities are S sub DS and S sub D1. 2/3. Why 2/3? 2/3 is the reciprocal of 1.5. 1.5 is 3/2. 2/3 is the reciprocal of that. Okay. So the idea is, if we consistently everywhere design for 2/3 of the maximum considered earthquake ground motion, if we consistently everywhere design for 2/3 of the soil modified MCE ground motion, then the 1.5 factor will, or let me go one step back. The 1.5 is the margin of safety, the lower bound margin of safety that we believe is available in all structures designed by the modern seismic code, which by common acknowledgement dates back to 1977 UBC, Uniform Building Code, the edition that followed the 1973 Uniform Building Code, the edition that followed the 1971 San Fernando earthquake. So we believe that buildings designed by the 1973 UBC or subsequent building codes are unlikely to collapse on us until earthquake ground motion equals and then exceeds 1.5 times the design earthquake ground motion of those days, which had a 90% probability of exceedance in 50 years. So anyway, so 1.5, think of that as a margin of safety available in your structure. So the idea behind this 2/3 is, if we consistently everywhere design for 2/3 of the maximum considered earthquake ground motion, the built-in margin of safety 1.5 would ensure that we would barely avoid collapse in the maximum considered earthquake. Okay. So that's what 2/3 comes from. AC7 does not really define a design earthquake except by saying that it is 2/3 of the maximum considered earthquake. Okay. The maximum considered earthquake is defined, and I will go there soon. So the S sub ds and S sub d1, which are derived quantities in AC7, are given directly in BNBC in S sub ds in table 6.C.4, S sub d1 in table 6.C.5. So the the quantities you need to define your design spectrum are given to you in that appendix. So these are S sub ds values. Again, you see that the the values. So the values are given for the different soil types and the various seismic zones. That's all that you can possibly need. And this is S sub D1. Okay. S sub D1 is S sub DS. Well, remember the basic relationship is S sub S is 2.5 times S sub 1. Which would mean S sub ds d1 is S sub ds times 0.4, that's 1 divided by 2.5 times f sub v over f sub a. This is the short period site, long period site coefficient divided by short period site. That should be obvious to you if you think a little bit. I don't have to spend time on that. Okay. Now, this I just said kind of in passing. Okay. So 1997 Uniform Building Code was the last edition of the UBC. And the UBC tends to be important because that was the dominant, for seismic design, that was the dominant model code in the United States. It was used in the western parts of the United States, including California, where we have a big seismic problem. UBC has also been used around the world for reasons I do not quite know, but in countries like Iran and so forth, it is still UBC after so many years of IBC. They're still doing UBC design. So anyway, in the UBC days, the design earthquake ground motion had approximately 90% probability of non-exceedance in 50 years, which amounts to a 475-year return period. So 475-year return period ground motion was the design ground motion of the UBC, and we did our seismic design to ensure life safety in that earthquake. Okay. Like to ensure life safety in the 475-year return period earthquake. Under AC 705 and the IBC, we designed to avoid collapse in the maximum considered earthquake, rather than to provide life safety in the 500-year return period earthquake. I would very much like that you realize that this major transformation happened as we went to the new generation of codes, IBC, based on AC7. Okay. We used to design to provide life safety in the 500-year return period earthquake. We now are designing to prevent collapse in the maximum considered earthquake, which I haven't defined for you yet. Okay. So now the maximum considered earthquake. This is defined in the NARP provisions. I think I have mentioned those National Earthquake Hazards Reduction Program provisions, which act as resource document for ASC 7 and the model codes. So the maximum considered earthquake is defined in that document, or was first defined in that document, as maximum level of earthquake ground shaking that is considered reasonable to design buildings to resist. Maximum level of earthquake ground shaking that is considered reasonable to design buildings to resist. This word reasonable makes this pretty useless as a definition. You cannot have something that's subjective as part of your definition. So this is at most a declaration of principle. Okay, that's what we want our maximum considered earthquake to be. Okay. This is the ground shaking that is considered reasonable to design buildings to resist. A two-part definition was built around that declaration of principle. The coast of California, the Pacific coast of California, is about the only part of the Earth's crust where seismologists know the seismic sources, and they also know the capabilities of the seismic sources, what they can generate by way of strong ground motion. And that being the case, some of the best of them together decided that the maximum considered earthquake ground motion for coastal California shall be the maximum magnitude earthquake, no, ground motion from maximum magnitude earthquakes on seismic faults with high probabilities of occurrence. In other words, in coastal California, the maximum considered earthquake is the largest earthquake that can be delivered by the known seismic sources. As simple as that. Okay? Since these seismologists know the maximum considered earthquake is the largest earthquake that can be delivered by the known seismic sources. This is also called the deterministic earthquake. In Bangladesh, you don't have to deal with deterministic earthquake because you don't have those seismic sources capable of delivering large ground motion. Now, in the rest of the country, where seismologists are nowhere near as confident that they know the seismic sources or their capabilities, some of the best of them together decided that the event that comes the closest to the deterministic earthquake of the western United States is a 2,500-year return period event. Okay? 2% probability of exceedance in 50 years. Okay? So remember, the design earthquake of the UBC was 90% non-exceedance. That means 10% exceedance in 50 years. Now we are talking about 2% probability of exceedance in 50 years, which is roughly 2,500-year return period earthquake. So this is the maximum considered earthquake for our purposes in Bangladesh. This is the 2,500-year return period earthquake, 2,475 years to be more exact. So we come back to the design spectrum or the design response spectrum of ASC 7. Nothing is changed except that we now know that it corresponds to the design earthquake of ASCE 7, and the design earthquake is 2/3 of the maximum considered earthquake, which I have defined for you. Okay, so the T sub L. Remember, to define the spectrum, we need S sub ds, S sub d1, which we talked about. T sub L is also needed. T sub L for the United States is mapped, as you see here. Okay, the value ranges from 4 to 16 seconds. We did the coloring in ASC7. It's a black and white map, and it looks like a contour map. I had the map colored just to make the point that these are not contour maps. you have 4 seconds and then 12 seconds. How do you interpret it? You cannot. It is either 4 seconds on that side of the line, or it is 12 seconds on this side of the line. On the line, you have to decide which value you want to take. So anyway, in Bangladesh, this complication doesn't arise. The T sub D, which takes the place of T sub L, has a fixed value of 2.0 second for all of Bangladesh. Okay, so we come back to the I think this is probably a good time for a break. It's 26 after. We'll come back at 31 after, but I will tell you right now that this portion today, I have a whole lot of slides, and chances are very high that even if I go up to 11 with the lecture, I will not be done, which is fine, which is something I anticipate. So I will continue tomorrow and then go to tomorrow's topic, which is a bit shorter. So between the 2 days will be okay. And probably tomorrow at 10:30 or so, I will start taking questions. It probably will not happen today. Yeah, it seems to me, considering I know how much I need to cover. Okay. Okay, so let's take, by now it's 27. So we'll be back at 32 after the hour. Okay. Thanks. Okay, it's time, I think. So I'll start. This is the BNBC spectrum that I have shown you. I have shown you all of this also, that T sub B corresponds to T sub 0 of AC7, T sub C corresponds to T sub S, T sub D corresponds to T sub L. Now the T sub C is exactly equal to the T sub S of AC705, and both are equal to S sub D1 divided by S sub DS, because at this point the S sub DS has to be equal to S sub D1 by T. The equation for the flat top is S sub DS. The equation for the descending branch is S sub D1 by T. Both have to be equal, which means this period has to be S sub D1 divided by S sub DS as it is. So T sub C and T sub S are no different. T sub D, however, has a fixed value of 2 seconds. T sub L has multiple values ranging from 4 to 16 seconds in the US. The T sub B is, I find, kind of interesting. So T sub 0, the counterpart of T sub B, is simply 20% of T sub S. AC7 tells you that. T sub 0 is equal to 20% of T sub S. And T sub S is equal to T sub C. But T sub D is not equal to that. T sub B is typically greater than that. And how the T sub B values were derived, I do not quite know. But I did want to present this to you. Okay, the comparison between the two. Now, BNBC gives you essentially equations for these branches. Okay, this ramp, the first branch, the second branch, and the third branch. So for all of those, BNBC provides equations. Four equations. Okay. I do not know what I need to. The eta is a damping. This is typically not part of, this is definitely not in US codes. This is not in most other codes that I'm familiar with. So when we talk about design spectra typically assume 5% of critical damping. Now, if you are aware that the structure you are dealing with has substantially higher or lower critical damping, then this eta gives you the choice of figuring out exactly how much damping you are dealing with and accounting for that in seismic design. US documents do not have an eta factor. 5% of critical damping is assumed. If it is very different, some people know there are ways of accounting for the higher or lower damping, but it is seldom done. Anyway, so for 5% of critical damping, BNBC tells you eta is equal to 1, so eta goes out of those equations. The S is the soil factor, as I mentioned to you. I think by now you know every other notation, so there is nothing to be. The only thing is that there is a limit, upper limit of 4 seconds beyond which the spectra are not defined. That is not the case in the US. We don't stop at 4 seconds. This table I showed you already enables you to construct the BNBC spectra. Everything you need is given in this one table. So I don't know that this table adds a whole lot to what we have discussed. I'm again making the point that this table is the same as that part. Okay. No difference. We just dropped the soil column. You're looking at the same table. The point I'm making again here is that the T sub S and T sub C are the same. T sub C here is the same as T sub S of ASC7. The T sub L of ASC7 is given on map. T sub D of here is 2.0 second, as you can see. The T sub 0 and T sub B are not the same. Okay. The T sub 0 is typically lower than T sub B, or T sub B is higher than T sub 0. So no, not a lot of new points made on that table. Now, when you plot this spectrum for the different soil types, so for each soil type, this C point B is defined, the point C is defined, the point D is defined. Okay, so if you construct the spectra for different types of soils, this is what the spectra look like. Okay, so this is S sub A, this is S sub B, this is S sub C, then S sub D, and then S sub E. There are questions about why A to B to C to D is not a uniform. Anyway, that's our questions I'll come to later. But this is what typically, not just the BNBC spectra, this is how spectra typically look like. Okay. So if you construct the BNBC spectra following the information that is given in BNBC, this is what you end up with. So the rest, the next few slides are just a repeat to show you the summary of what the appendix provides, and there is nothing new there. Okay, the zone map you have seen. The zone map gives you the Z values. There is a table to go with the map. that for every significant community in Bangladesh will give you the Z value. The Z is we'll come back to that. Let me not go into. So then in table 6.C.1, BNBC gives you the S sub S and S sub 1 values for the different seismic zones. This table, sorry. So the next table gives you F sub A values for the different seismic zones. Then the F sub F values, F sub B values for the different seismic zones. Then the S sub DS, the parameter that we have to calculate in ASC7, that is given to you ready-made in table 6.C.4, and the S sub D1, which we also have to calculate at great labor, is given to you in table 6.C.5. Okay. Now, we go into part 2, a slightly different topic, seismic zone versus seismic design category. Seismic zones were in the Uniform Building Code, and that is the last time in the US that we have used seismic zones. All the editions of the IBC have been based on seismic design categories, not zones. Okay. So UBC had zones 0 through 4, except there were 2A and 2B. The 0 was non-seismic, 4 was the highest seismic. Anyway, let's not get back there. So back in those days, the zone in which a structure was located determined the height limits for a structural system, like bearing wall systems could not be taller than 160 feet in seismic zone 4. The zone determined the level of analysis you had to do as the basis of design. In seismic zone 4 or 3, certain structures could not be designed based on equivalent lateral force procedure. The zone brought with it prohibitions on some structural systems, some things you could not do in high seismic zones. Anyway, the zone determined the limitations and restrictions on seismic design, or even what kind of design we could do. That role now has been taken over by the seismic design category, which is a function of definitely the seismic hazard at the site of the structure, which is what the seismic zone was all about, but also the occupancy of the structure, whether it's a hospital or a police station or an office building or a school, and very importantly, the soils at the site of the structure. So the seismic design category is a function of soil modified ground motion at the site of the structure and the occupancy of the structure. Very, very different. Okay. So the occupancy part is defined in table 6.1.1 of BNBC 2020. This closely follows a corresponding table in ASC 7. So we have occupancy category 1, 2, 3, and 4. 4 are essential facilities or hazardous facilities. 1 is miscellaneous occupancy, as we call it, no life safety, unimportant buildings where no life safety is at stake. and 2 are standard occupancy buildings. The apartment building, the office building, all of those is occupancy category 2. Okay. So occupancy categories 1 through 4. The seismic design category must be determined first based on short period ground motion S sub ds by this table that is part of ASC 7. Okay, so we have the occupancy category here and S sub ds here. S sub ds, I remind you, is soil modified ground motion. So the ground motion is here, but the soil is also here. The seismic design category is a function of three things. The table gives you design categories A through D. I tell you that there is no design category A in Bangladesh because for design category A, S sub ds has to be less than 0.167, and you do not have values that low anywhere in the country. So you determine seismic design category based on short period ground motion. You redetermine the seismic design category of the same structure now based on long period ground motion S sub D1 from this table, and you take the worst of the two. Based on short period ground motion, your design category turns out to be C, but based on long period ground motion, it turns out to be D. Your design category is D, not C. Under certain circumstances that are listed in ASC 7, you are allowed to determine seismic design category based on short period ground motion alone. You don't have to look at long period ground motion, but that is only under certain conditions. Okay. Now, the tables give you A, B, C, D, but then there are those notes to go with the table. And the notes we have translated into a little table. The notes actually say, if your site is located where the mapped long period ground motion can be larger than or equal to 75% of gravity. Okay. If your site is located where S sub 1 can equal or exceed 75% of G, which can happen only in the vicinity of faults that can generate large earthquakes. Then non-essential facilities, occupancy categories 1, 2, and 3 are design category E, and essential facilities are design category F. So a hospital close to a fault that can generate large earthquakes would be design category F, as in Frank. Okay, so in Bangladesh, you do not have design categories E or F because you do not have large faults capable of generating earthquake ground motion of 75% or larger. Okay. So there is no design category A, there is no design category E or F, so your design categories are B, C, and D, just so that you know. Okay, the zone map, the BNBC gives you, like so many other things, the design categories in this table. You don't have to do anything. Okay, so the site class and the seismic zone of your structure and the occupancy of your structure. If you know your occupancy, so let us say an office building in Dhaka, so that would be zone 2. If your site class is D, which is mostly true in the newer parts of Dhaka, then your seismic design category is D. Okay, occupancy category 2, zone 2, site class SD. your design category is D. So most buildings in the newer parts of Dhaka, you will see the design category is D based on this table. Very, very important table in BNBC. They essentially give the design category to you. Okay, building configuration, very important topic. AC 705 has a table of horizontal irregularities, and those are torsional irregularity, extreme torsional, re-entrant corners, diaphragm discontinuity, outer plane offsets of the seismic force resisting system, and non-parallel seismic force resisting systems. We will talk a lot about them, particularly tomorrow, so every detail will become clear. But for now, those are categories of horizontal irregularities that are recognized in AC7. BNBC has a, how do I want to say it? BNBC has narrative descriptions of many of these irregularities, torsional, re-entrant corners, and these are actually definitions that you see. Diaphragm discontinuity, outer plane offsets, non-parallel systems. So the categories 1 through 5 that we saw here are described for you, if not defined for you. Some cases it is defined for you by BNBC in section 25531. I will not read them today because tomorrow's seminar I want to devote almost entirely to this topic of structural irregularity. This is why I'm not, it doesn't, BNBC is not covering any new ground. Otherwise, I would have gone there. But anyway, so there is horizontal irregularity. Initially, we used to call them plan irregularity, and then there is vertical irregularity. Okay? That the categories are stiffness irregularity or sob story, extreme sob story, 1A and 1B. 2 is weight or mass irregularity. 3, vertical geometric irregularity. 4, in-plane discontinuity in vertical lateral force resisting elements. 5, discontinuity in lateral strength or weak story. 5B is extreme weak story. Okay, those are the different categories of vertical irregularities in a structure. Again, BNBC describes those, sometimes defines those, or oftentimes defines those. The definitions are no different from those in AC7, and I will discuss this entire topic tomorrow in detail. It's a very important topic in my opinion, and I would like to give it the time that it deserves. Yeah. Then, as you see, methods of analysis. This we from the beginning of seismic design, as I understand it, we have made a big deal of these analysis procedures, whether the equivalent lateral force procedure that we use much of the time good enough for certain structures. Do we have to do dynamic analysis? And so on and so forth. Equivalent lateral force procedure was allowed to be used under restrictions, as you will see very clearly in BNBC 2020, and I'll point those out. But in the latest US codes, in AC 722, which AC 722, the electronic version has been released. Paper copies are still not available. It will be sometime this month. Be that as it may, in this document, equivalent lateral force procedure will be allowed for basically everything. As time has gone, we have found that in some ways it is superior to the modal response spectrum and so forth that we thought were the way to go. So that's a complete reversal of a long history. But obviously we are not there. He will probably stay with this code AC 705 for years to come. So I don't want to bias you or confuse you. That's not my purpose. All I'm trying to point out is that in many, obviously you will, I think you are all realistic enough to expect that there are changes. AC 705 was succeeded by AC 710, then AC 716, then AC 722. Each edition there are significant changes, this time probably more than ever before. But when it comes to analysis, this is something very drastic, in my opinion, that has now that we have now put into AC 722. This is why I thought that I would mention it. Anyway, AC 7 has a so-called simplified analysis, which is in a standalone section 1214. That method, I'm kind of glad BNBC has not included. That simplified analysis, there are a number of restrictions that a structure has to meet before it becomes eligible for simplified analysis, and some of those conditions are pretty onerous, not easy to satisfy. That takes away from the simplicity of the procedure itself. Equivalent lateral force procedure, which we will do today, section 12.8 of AC 7257 of BNBC. Modal response spectrum analysis, I will do that next Monday. 12.9, 2.5.9 of BNBC. Then there is linear response spectrum and non-linear, not spectrum, linear response history and non-linear response history procedures. Okay, I will not go there. Linear response history analysis, I do not believe gives you anything that you cannot get out of modal response spectrum analysis. So I do not know. I personally am not very high on that. Nonlinear response history analysis, on the other hand, is pretty much the state of the art. That's about as far as we can go with analysis. Response history analysis simply means that you subject the base of your structure to acceleration histories of ground acceleration or ground acceleration as a function of time. And these time increments have to be very, very small for you to have accurate analytical results. So the base is subjected to a history of ground accelerations, and we compute
Ghosh, you can unmute yourself now. Dr. Ghosh. I muted you because there was some leakage.
Okay. So where should I? How far did I go?
You were explaining the nonlinear, the response
Yeah.
tree.
Okay. Yeah. So uh, response history analysis means that you subject the base of your structure to a history of ground accelerations. Ground acceleration as a function of time, so we feed pairs of acceleration and corresponding time. And these time increments have to be very small for us to get accurate results. The structural response, whether it is displacement at the roof level, displacement at some other level, or force in a certain member, whatever we want to analyze for, those are obtained by structural dynamics, definitely using a computer program. This is way beyond anything we can do by hand. The difference between elastic and nonlinear response history analysis, linear and nonlinear, is that in the first case of linear response history analysis, we assume that the structural members remain elastic throughout its seismic response. In the second case of nonlinear time history analysis, we recognize reality and concede that certain regions of certain structural members will go inelastic in the earthquake ground motion that we are analyzing for. Now, the inelastic behavior of these regions, the load displacement part, has to be modeled. And the success of nonlinear time history analysis, how good the results are, depends on our ability to properly model the load displacement behavior of these inelastic portions. Okay, so that's very briefly what we are talking about. Nonlinear response history analysis has undergone a lot of work in ASC7, and starting with how do I want to say it, in ASC7 chapter 16, you will find pretty much the state of the art of nonlinear response history analysis. I do not recall that there have been all that terribly many improvements in 2019, but 16, there was a huge amount of work done. So if you have an interest in that subject, I think that is the place you should go to, chapter 16 of ASC 716. Okay. Now, nonlinear static analysis was something that it was never important, but it was kind of seemed to be catching on way back in the, I would say, 70s, 80s. And then it not only didn't catch on, it has totally fallen out of fashion. And our codes do not have them anymore. In the military document that we we do put them under contract, that has been the nonlinear static has still been maintained, but AC7 does not have nonlinear static analysis. IBC doesn't. Anyway, BNBC 2020 has spent a lot of time on nonlinear static analysis. This is something I will not go into. you probably have more familiarity with it than I do. In any case, I did want to mention that the procedures are somewhat different. The simplified analysis is not in BNBC. Nonlinear static analysis is not in AC7. But the main things, equivalent lateral force procedure, the modal response spectrum analysis, and elastic and nonlinear time history analysis, those are common between the documents. Now, AC7 has a pretty elaborate scheme for figuring out or to tell you when you can do static analysis and when you have to do dynamic analysis. Okay? So let us take a look at that. If the design category of your structure is B or C, then equivalent lateral force procedure is always permitted. You never have to do dynamic analysis. Okay? If, however, your design category is D, E, or F, and these are, I think, this definitely is more US than anything else. Still, let me give you a complete picture what AC7 tells you. So if you have light frame construction here in the US is wooden studs with some kind of sheathing on the studs. The sheathing can be made of wood or it could be plasterboard or it could be whatever. And these days the wooden studs are being replaced by cold form steel studs. So this is lighter construction. Irrespective of height, irregularity or anything, light frame construction, you can do equivalent lateral force procedure, never dynamic analysis. Dynamic analysis is never required. Okay? If you have risk category 1 or 2 building less than or equal to 2 stories in height, risk category 1 or 2, that means no schools, no hospitals, and less than or equal to 2 stories, then equivalent lateral force is always permitted. Okay? If you have other buildings, risk category D, E, or F, that are not in this category or that category, then the big dividing line is the structure less than or equal to 160 feet or more than 160 feet? Sorry, I forgot to or didn't think of translating into metric. 160 feet would be, I don't know, 50 meters, a little bit more. Anyway, so if it is a structure less than 160 feet, less than or equal to, which is the vast majority of structures, then among the different types of irregularity that we have, remember 5 types of horizontal, 5 other types of vertical irregularity. Some of those irregularities I will call quote unquote bad irregularities. And if your structure that is no taller than 160 feet has any of those bad irregularities, then dynamic analysis would be required. What are the bad irregularities? Horizontal type 1A and 1B, torsional and extreme torsional. Structures with the vertical 1A, 1B, that is soft story and extreme soft story. 2 and 3, I don't remember without checking. Anyway, so a structure no taller than 160 feet, if it has any of those bad irregularities, you shall do dynamic analysis. if a structure no taller than 160 feet does not have any of those irregularities, even if it has other irregularities, you shall be able to design on the basis of equivalent lateral force procedure. If it is a structure taller than 160 feet, now you can do equivalent lateral force procedure only if there are no structural irregularities, good or bad, no irregularities, and also the period of the structure is less than 3.5 times the transition period that we have been talking about, S sub D1 over S sub DS. S sub D1 over F sub DS is typically about 0.5. Very rough figure, 0.5. So 3.5 S sub ds of 0.5 would be 1.75 seconds. T of 1.75 seconds would be the period of a 17-18 story frame building. So we are saying shorter buildings can be designed using equivalent lateral force procedure. Taller buildings, you have to do dynamic analysis. Okay. Now, a design category D, E, or F building that is taller than 160 feet, if it has structural irregularities, or even if it doesn't have structural irregularities, if the period is equal to or larger than 3.5 times the transition period, then you will have to do dynamic analysis. Okay. So this is a bit elaborate, but very precise. It will tell you when you have to do dynamic analysis. In BNBC, this is what you have. ELF is allowed, provided both of the following conditions are satisfied. The building period in the two main horizontal directions is smaller than both 4 times T sub C and 2 seconds. I have added T sub C is our T sub S, which is S sub D1 over S sub DS of AC 705. Okay, 4 times T sub S. So AC 7 had 3.5 times T sub S. This is 4 times T sub S. Okay, we are in the same boat. So the building period in the two main horizontal directions is smaller than both 4 times T sub C and 2 seconds. It has to be smaller than 2 seconds. Okay. And the other condition is the building does not possess irregularity in elevation as defined in 2553. No vertical irregularity. That's kind of interesting. Okay. No vertical irregularity. So those are the conditions under which ELF will be allowed by BNBC 2020. It's a little different from AC 705. Okay. Now we start getting into the equivalent lateral force procedure. AC7, in AC7, the design base shear V is this coefficient C sub S, seismic response coefficient, times the effective seismic weight of the building. Okay. Now this seismic coefficient C sub S and spectral acceleration S sub A, those are closely related, and the notations are used differently by ASC 705 and BNBC 2020, making it very confusing to somebody like me. But I would like to point these things out as I go. Anyway, so AC7V, the design base shear is C sub S the seismic response coefficient multiplied by the building weight, effective seismic weight, the seismic weight of the building. Okay, W is the seismic weight of the building, and the idea is it is the weight of the building at the time the design earthquake hits. Okay, so when a design earthquake comes, if it is a storage facility, it is extremely unlikely that the material that is stored will not be there. Okay, so in storage facilities, we typically include a portion of the design live load in the seismic weight, and so on and so forth. So the point is the seismic weight is not the same as weight, and ASC 705 defines it very specifically in this section. So does BNBC, but the definitions are different, as I'll show you. So ASC 705 definition of effective seismic weight, as I'm calling it, okay? Total dead load and applicable portions of other loads. Total dead load, of course, and applicable portions of other loads. So applicable portions of other loads are 25% of storage live load. There are two exceptions to that. So if it is a storage facility, we will include 25% of the live load in seismic weight. Minimum 10 pounds per square foot partition load. We go for lighter partitions. Weight of permanent equipment, 20% of uniform design snow load, where flat roof snow load exceeds. That is a very important component, but not for you, so let me not spend time here. And then weight of landscaping and roof gardens. So if you have a garden on your roof, the weight of that has to be included in the seismic weight. Seismic weight of BNBC. Seismic weight is the total dead load of a building, of a structure, including partition walls and applicable portions of other imposed loads listed below. So very similar to AC 7, except dead load, it says including partition loads. And I believe those are fixed partitions that are being talked about. So applicable portions of other imposed loads, those are for live load. This is all different from AC7. From live loads up to and including 3 kilonewton per square meter. 5 is 100, 3 is 60 pounds per square foot. So live load to and including 3 kilonewton per square meter, a minimum of 25% of the live load shall be applicable. So even in residential occupancies, it would include a portion of the live load. For live load above 3 kilonewton per square meters, a minimum 50% of the live load shall be applicable. Yeah, this is quite different from ASC 7. Total weight of permanent heavy equipment or retained liquid or any imposed load sustained in nature shall be included, where the probable imposed loads at the time of earthquake are more correctly assessed. So where the probable imposed loads at the time of earthquake are more correctly assessed, the designer may go for higher percentage of live load. So I don't know. There is a significant preoccupation with live loads that I do not understand. As you saw, AC 7, we include 25% of the live load for storage facilities, and that's it. Okay. Here is 25% of everything, 50% of all occupancies with more than 60 pounds per square foot. And then it says you will do even higher. Yeah, anyhow. Okay, see the design response spectrum of SC7 you have seen 10 times by now. The point is, the reason I showed you again is when we do the equivalent lateral force procedure, we modify the elastic response spectrum. This is the elastic design response spectrum of ASC7. Design level, elastic spectrum. Okay. Now, when we are using the equivalent static approach, we make a number of modifications to the elastic spectrum. First thing is we eliminate the ramp. The flat top is extended all the way back to 0 period. That's modification number 1. We make 4 modifications. One is this, elimination of the ramp. Modifications number 2 and 3, we lower the elastic spectrum by the response modification factor R, and at the same time raise it by the importance factor I. Again, we lower the elastic spectrum by the response modification factor R, and we raise it at the same time by the importance factor I. That is the division by R over I that you see in the picture. Okay, those are steps 2 and 3. The modification number 4 is the descending branch, or this third branch, 1 over T or 1 over T squared, will give us 0 base shear at a long enough period. And we do not want to design for 0 or very low base shear. So we impose minimum values of design base shear. In ASC7, there are 2 different minimum values. One is 0.44 S sub ds times I times W, 0.44 S sub ds short period design spectral acceleration I times W, but never any lower than 1% of W. So if S sub ds is very small, this can be lower than 0.01, but we will not take it ever any lower than that. Okay, 0.44 S sub ds I times W, that is applicable in all seismic design categories. Okay, there was a period in the US, short period, when this minimum was eliminated from ASC7, but it was brought back relatively quickly. Yeah, and so it was there before, it has been there since. There was only an interim period when we thought we could get rid of it. Okay. The other minimum is where our site is located in a relatively high seismic area, where the mapped long period quantity S sub 1 is larger than or equal to 0.6 G. This is the rough equivalent of old UBC zone 4. And there we have the second minimum, 0.5 S sub 1 divided by R over I multiplied by W. Okay, where both of those minimum values apply, you have to use both. The obviously the larger minimum will control. Where both apply, the higher minimum will control. I do not know that we will be in Bangladesh, we will be using that number all that much because S sub 1 larger than zero point 0.6 is not. I could go back. I don't know if it is there at all or if it is, how common it is. S sub 1 larger than zero point 0.6. I can probably check right now while I'm speaking. S sub 1. No, there is no S sub 1 larger than zero point 0.6. So this second minimum is moot for you. So again, the point is when we do the equivalent static approach, the four modifications to the elastic spectrum are the ramp is eliminated, the elastic spectrum is lowered by the response modification factor R and at the same time raised by the importance factor I, and then we impose minimum design base shear of 0.44 S sub ds times I times W, but no lower ever than 1% of the seismic weight. Okay. So we try to go from AC7 to BNBC. This is the spectrum that you have seen a number of times now, BNBC spectrum, defined at those points, TB, TC, TD. Anyway, MCE level C sub S is ordinate of normalized acceleration response spectrum. The C sub S is S sub A divided by PGA on rock. The C sub S of BNBC 2020, when it is MCE level, as the title tells you, MCE level C sub S is S sub A divided by PGA, peak ground acceleration on rock. This is the relationship between C sub S and S sub A. It will come back in various forms. You have seen these equations defining the BNBC spectra. You have seen this table that gives us specific values for the numbers we need to plug in here. Okay, the S value, T sub B is what, T sub C is what. So with those equations and the table, we can construct the BNBC spectra that you saw a minute or two ago. Okay, I hope you are following me. So this is the generalized spectral shape. These are the equations of the various branches of that generalized spectral shape. And then this table gives us the numbers to go into those formulas for various site classes and so forth. So when we put the values in the table into the equations for the spectra, we get the spectra for the various site classes, and this is what they look like. Okay, so this is what we are dealing with in BNBC 2020. On the y-axis is C sub S, which I pointed out is S sub A divided by PGA on rock. So far, everything is MCE level. MCE level C sub S is MCE level S sub A divided by MCE level PGA on rock. On the x-axis, on all spectra, it is the period of the structure, T. Okay. At the beginning of AC7 equation, it is worth going back. I started big, bold. V is C sub SW. C sub S is seismic response coefficient. Okay. In BNBC 2020, V is S sub A times W, not C sub S times W. These are the confusing parts. Both documents use C sub S and S sub A, but use them slightly differently. And I spent an inordinate amount of time figuring this stuff out because it's not, anyway, I hope it will help you when I say these things and I put enough on the slides. So BNBC 2020, V is equal to S sub A, the spectral acceleration multiplied by W. The spectral acceleration is 2/3 Z I over R C sub S. This is C sub S of BNBC 2020, which you know is S sub A divided by PG on rock. Okay, we said that here. C sub S is S sub A by PG on rock. So MCE level C sub S is ordinate of normalized acceleration response spectrum is equal to MCE level S sub A divided by MCE level PGA rock. Nothing different from what I just said. So MCE level C sub S is MCE level spectral acceleration divided by MCE level PG on rock. Okay. Now, design level S sub A, okay, is the MCE level C sub S, this quantity, multiplied by 2/3 to go down from maximum considered earthquake to design level. And as in AC7, we divide by R. We lower the spectrum by R and we raise it by I. So design level spectral acceleration is the MCE level C sub S that we have been dealing with so far. Okay. Multiplied by 2/3 to bring it down to design level, and then modification by R and I. The Z is, as I said earlier, is MCE level PGA on rock. Okay, so the C sub S is MC level S sub A divided by MC level PG on rock. Z is MC level PG on rock. So Z times C sub S is actually S sub A, MC level S sub A. So all we have done here is taken MC level S sub A multiplied by 2/3 to get it down to design level and then make those I over R modification. So hopefully if you look at this part, it will I spend quite a bit of time with this and hopefully you will gain something from it. Okay. So in your ability to relate AC7 BNBC and also what is happening with BNBC. So V is equal to S sub A times W, and S sub A is given by 2/3 ZIR times C sub S. Okay. We will run some numbers. I think this is the best way to get anything across. So an intermediate moment frame building in Dhaka on soil type SD. Residential apartment building, we will take I equal to 1. S is 1.35 for SD soil, 1.35. Dhaka is in zone 2. You have seen Z is 0.2. Okay. TB, again from the same table. TB, Dhaka SD, TB 0.2, TC 0.8, TD 2. Okay, 2.8 and 2. So residential apartment building I is equal to 1. SD soil S is 1.35, zone is 2, Z factor is 0.2, TB is 0.2 second, T sub C is 0.8 second, T sub D is 2.0 second. Okay. So the spectrum has the 4 branches, the ramp building up to the flat top, the descending branch, and then the 1 over T squared branch. For the first branch, this is the equation. Okay, if you go back, you'll see the same equation. We will take eta equal to 1 for 5% of critical damping. So that will make the equation S plus 1, 2.5 eta minus 1 would be 1.5, and then T over T sub B. This is the same as that with eta equal to 1. So S is 1.35, and then the remainder has been left as is, and that would mean 1.35 plus 1 plus 1.5 divided by 0.2 is 7.5 period. Okay. At T equal to T sub B, which is 0.2 second, which is the head of the ramp, C sub S is 1.35 times 1 plus 7.5 times 0.2. And that, so 1 plus 7.5 times 0.2 is 2.5. So at T sub B, C sub S comes out to 3.375. Okay, that's C sub S. S sub A, which is 2/3 Z I over R times C sub S. We saw it on the previous slide. So 2/3 Z is 0.2, R is 5, intermediate moment frame, I is 1, C sub S, we just found 3.375. So S sub S comes to 0.09. That is the spectral acceleration, 9%. Okay, or 0.09. Anyway, it's a number, spectral acceleration. Remember, our operating equation is V is equal to S sub A times W. In BNBC, that's what it is. Okay, V and W have the same units. Okay, it is the unit of weight. Here it is skips, you have kilonewton or whatever, I don't know. So the S sub A is a number, doesn't have a unit. Okay, so it was 0.09 at the end of the ramp. Now we do the ramp. T sub T between T sub B and T sub C. This is the beginning of the ramp. This is the beginning of the flat top. This is the end of the flat top. Okay, the flat top portion. This is the equation. 2.5 S times eta. Eta is 1 for 5% of critical damping. S is 1.35 for our particular soil. So C sub S is 2.5 times 1.35, that is 3.375. Okay, this is the flat top. At T equal to T sub C equal to 0.8 second, C sub S remains 3.375, irrespective of period. So S sub A now, spectral acceleration 2/3 Z I over R C sub S is 2/3, Z is 0.2, R is 5, I is 1, and C sub S is 3.375. So that comes to also 9%. At the beginning of the flat top, S sub S is 9%. At the end of the flat top, S sub S is 9%, as it should be. Otherwise, it wouldn't be a flat top. Then we go to the descending branch, T between T sub C and T sub D. This is the long period transition period of 2 seconds. Yeah. Okay, so T between T sub C and T sub D, this is the descending branch. T sub C has a value of 0.8 second in our case. T sub D is 2 seconds. So C sub S from this equation, taking eta equal to 1, is 2.5 the soil factor T sub C divided by T. 2.5 soil factor is 1.35, T sub C is 0.8 divided by T. That comes to 2.7 divided by T. So at T equal to TD equal to 2, that is at the end of the descending branch, C sub S would be 2.7 divided by the period of 2 seconds, that is 1.35. So S sub A would be 2/3 0.2 I upon R of 5 times C sub S of 1.35. That comes to 3.6%, 0.36. So at the beginning of the flat top is 9% S sub A. That means design base shear will be 9% of the seismic weight. At the end of the ramp, it is the same thing, 9%. At the end of the descending branch, when we hit T sub D, the S sub A is down to 0.36 from 0.9. And then we go from the beginning of the 1 over T squared branch to the, remember, BNBC spectrum doesn't extend beyond 4 seconds. So the segment between 2 second period and 4 second period is what we are looking at now. The formula is this: eta is equal to 1. So C sub S is 2.5. The soil factor S, eta goes away. T sub C, T sub D divided by T squared. 2.5, S is 1.25. No, this is a mistake. This is 1.35, right? That doesn't change. I hope the number is right. I don't know. I'll check that. So please note that I went over it twice, at least yesterday, didn't notice that. So I'll make a note and correct it. Somehow these things bother me, but I cannot do better, unfortunately. Anyway, 2.5. The soil factor is 1.35. T sub C is 0.8. T sub D is 2 divided by T squared. And that apparently came to 5 over T squared. It will probably be a little bit different. So at 4 seconds, C sub S would be 5 divided by 16, or 3.125. S sub A then would be 2/3 the Z of 0.2, I of 1, R of 5, C sub S of 3.125. That comes to 0083. That's 0.83%. Okay, it will be a little bit different. It will be slightly higher because this was 1.35. Now the minimum, this check is not necessary, but we did that. The minimum, remember, in AC7, 044 S sub ds times I. And when BNBC referenced AC702, it said you shall keep this minimum. So that applies to BNBC as well. 044 S sub ds times I, that is 044 this S sub ds is 2/3 Z times S. Okay, that if you go back a page or two, you will find this relationship. The 044 2/3 0.2 S of 1.35, here it is correct, I of 1, that is 00792, which is 0.79%, which being less than 0.83%, that is okay. So we cannot go below 0.79%. Note this check is not required by BNBC 2020. Okay. We ran numbers also by ACE7. So initially, T is between 0 and T sub S. Okay. Remember, in AC7, there is no ramp. The beginning of the flat top is at 0 period, and the flat top ends at transition period T sub S, S sub D1 over S sub DS. Okay. That T sub S is also T sub C of BNBC, in our case, 0.8 second. So the flat top of AC7 is given by this expression. C sub S, in that case, C sub S is what we multiply the weight by to get the base shear. Okay, this is not the same C sub S of BNBC. You have to, this is why I ran the numbers and are discussing the subtleties so much. So C sub S is S sub ds over R over I. For zone 2 soil type SD, S sub ds is 0.45 from BNBC. So S sub ds is given in that table. So C sub S is the S sub ds of 0.45 divided by R of 5 and I of 1, and that gives us 9%, just as BNBC did. This is the flat top. The base shear is 9% of seismic weight. Okay, this was called S sub A in BNBC. Then from the end of the flat top or the beginning of the descending branch to the end of the descending branch. And our descending branch ends at the long period transition period of 2 second fixed. For zone 2, soil type SD, BNBC gives us S sub D1 of 0.36. So C sub S would be, remember the AC7 equation for the descending branch is C sub S is S sub D1 divided by RT. C sub S1, I'm sorry, C sub S is S sub D1 divided by RT. S sub D1 is 0.36, R is 5, T is T, so 0.36 divided by 5 gives us the 0.072. So at T of 2 second at the end of the descending branch, the C sub S comes to 0.036, exactly the same as under BNBC. I told you the two approaches give you the same numbers. So now beyond the long period transition period of 2 seconds, okay, in AC7 you can go as far as you like. In BNBC you are restricted to no more than 4 seconds. C sub S of AC7, this branch is defined by S sub D1 T sub L divided by R over I T squared. S sub D1 is 0.36 from the previous page. T sub L is 2. R sub I is 5 T squared, that is 0.144 T squared. So at T of 4 seconds, where we calculated the S sub A by BNBC, C sub S is 0.144 by 4 squared, which is 009, which is 0.9%. Minimum is 0.79%. This is a little bit different from the 0.83% of BNBC 2020, but we found a mistake in the BNBC. 0.83%. Remember the 1.35 versus 1.25. So it will come closer probably to the same number. Okay, so I hope you find these numbers beneficial. I always do. And okay, so let me, a few minutes left, let me cover a little more ground, and then the rest will be left for tomorrow. So in the base shear formulas, V equal to S sub A times W, or V equal to CSW in AC7, the S sub A or C sub S varies with 1 over T. Unless you are at the flat top, the spectral acceleration varies with 1 over T or 1 over T squared, as the case may be. So without a period, we cannot calculate the base shear, and without a base shear, we cannot design our structure. So we cannot determine period. So this is a classic chicken and egg situation. And because of that, our codes have always given us approximate base shear, approximate period with which to get started. And that is denoted by T sub A. So you can start your seismic design by T sub A. And once you have gone part way through the design, you can refine your period estimate if you so choose. Period can then be estimated by any rational procedure that is in conformance with the principles of mechanics. Okay, and when you do rational computation of period, it always comes out to be larger than the approximate period, so you can get to lower your design base shear if you so choose. But the starting point is the approximate period. Okay. So period can be calculated by approximate formulas or by rational analysis using structural properties and deformational characteristics of resisting elements in a properly substantiated analysis. Okay. The approximate period formula is the T sub A is equal to a coefficient C sub T times the height, building height raised to the power X in AC7, M in BNBC 2020. Okay. So C sub T times height raised to the power something. This tells you that the approximate period cannot be, quote unquote, the real period of the structure. Okay. Because it is a function only of height. Let us say we have a structure that is 500 foot long and 100 foot wide, a very elongated structure, 100 feet by 500 feet. In the 100 feet direction, the building is reasonably flexible. The well, let's take the longer. In the 500-foot direction, the building is extremely rigid, extremely rigid. It so I mentioned to you yesterday, okay, flexible buildings have long periods, rigid buildings have short periods. Okay. So in the 500-foot direction, the building has a much shorter period than in the 100-foot direction. That is common sense, right? But by the approximate formula, you will calculate the same period irrespective of direction. So that tells you that the approximate period cannot be, there is no way it can be the real period of the structure. The sole purpose of the approximate period is to get us started, but also T sub A is designed to be lower than the real period. The idea being, if we don't later refine our period estimate, our design will still be on the conservative side, because the shorter the period, the larger the design base share. Okay? That the design base share is inversely proportional to period or period squared. So the shorter the period, the larger the design base share. So if we want to be conservative in design, if we want to remain conservative when somebody does not refine the initial period estimate, then T sub A has to be smaller than the rationally computed period. Okay, the values of C sub T and X are given. So there is a set of values for moment resisting frames of steel. There is a set of values for moment resisting frames of concrete. Then a set of values for eccentrically braced steel frames. And then for all other structures, concrete shear wall structures, for instance, the C and C sub T and X are given. Okay, so in our units it is 0.02 height raised to the power 3/4. In your units the power doesn't change, it is 3/4, but the 0.02 becomes 0.0488. So that's just the unit. For masonry or concrete shear wall structures, there is an alternative approximate period formula. Alternative to 0.2 height raised to the power 3/4, alternative to this line. I would caution you against using this formula. I first of all, I wouldn't go into it, it's complicated, but more importantly, we have found that the formula is deficient in a couple of significant ways. And later times, we have made some modifications to this formula. So my advice will be, don't try to use that one. Okay. Now, a rationally computed period. You can calculate period by any rational procedure as long as it is in keeping with the principles of mechanics. All of that is true. But rational period computation depends on your stiffness assumptions. If it is a concrete building or a masonry building in particular, by taking cracked rather than gross stiffness, and by taking cracked stiffness low enough, you will be in a position to calculate a period as long as you want it to be, which then will give you a design base shear as low as you would like to design for. That is not the point of that's not the purpose of rational period computation. That actually defeats the purpose. It is not supposed to be a license to lower your design base share just as much as you would like. So that being the case, there are limitations, there are restrictions on rationally computed period. You can compute it as long as you want it to be, but for design purposes, you shall not take it any more than a multiplier times the approximate period. So rationally computed period is tied to the approximate period. Actually in AC7 seismic design or BNBC seismic design, you never get away from the approximate period. Even when you do dynamic analysis, the results of dynamic analysis have to be scaled to the results of the static analysis, either 100% or some percentage. But the dynamic analysis is tied to static analysis, and static analysis is dependent on this approximate period. Even when you do rational period computation, you do not get away from that. The only time you are independent of this approximate period is when you are doing nonlinear time history analysis. Then you are not tied back, but that's the only case. Okay. Now the C sub U in BNBC 2020 is a fixed 1.4. Okay. So you cannot go, no matter how much you have calculated your period to be, you cannot take a period more than 140% of T sub A. Now that is true only when it comes to the design forces. When it comes to displacements, this limitation that T sub T cannot be taken any longer than C sub U times T sub A does not apply. And that we will discuss when the time comes. Okay. But keep in mind, this restriction is for force-related quantities, not deflections. Now, in AC7, C sub U depends on the value of S sub D1. And for in low seismic areas, we can go up to 170% of the approximate period. Okay. In BNBC, the range of S sub D1 is from 0.8 to 648. 0.8 is down here. So if BNBC decided to follow SC7, we could have utilized 170% of approximate period, but BNBC, as I said, has a fixed upper bound 1.4 times T sub U. Okay, I see it is 11. I have significantly more left than I expected, but now I will let you go. 11 o'clock, I think, should be the limit. Let me see what happens tomorrow. Okay, Bodhi, I think, unfortunately, I probably better quit.